Hi, welcome to a new lecture of Math-S400, Mathematics and Economic Modeling. Today we're going to see the concept of a function, and we're going to see what it means for a function to be continuous in the sense of convergent sequences. So let's go to the whiteboard. Okay, so we're going to define a function that takes a vector in Rk. Okay, so let's x be a vector in Rk. And we're going to define a function as something where you put in a vector and what comes out of it is going to be a number. Okay, so you can think of a function as some kind of a machine. So you put vectors in the machine and what comes out of the machine is simply a number. So often we depict this as having two sets, Rk, which is a space of all vectors, and then you have R, and then you take a vector in X and we map it to some number Y, which is here f of, denoted by f of x. Okay, so what's particular about functions? Well, if you take two vectors x and z and they are the same, then f of x will also be equal to f of z. So in other words, if I put two vectors in the machine and they are the same vector, then each time you put in the same vector, we will get out of the machine the same number. Right? So it's impossible that you put in two times the same vector and get out of the function a different number. Right? So this is something that's very particular to functions. If you put in the same thing, then you get out of it also the same thing. So the set of all vectors that you can put inside a function, this is called the domain of the function. Okay, and then all the numbers that you can get out of a function, this is called the range of the function. Okay, so a function we normally denote this as f, and then you have 2 points, and then we put the domain, which we will call d, then an arrow, and then what you get out of it here, it's going to be a number. Okay, so here d is a subset of Rk, so what you put inside are vectors. All vectors in d can be put inside the function, and what you get out of the function is going to be a real number. And then the range is going to be all the numbers y and r, such that I can find a vector in d such that f of x is going to be equal to this number y. Okay, so basically the range is all the numbers here that you can get when you put something inside the function f. And you also denote this by f of big D, right? So here the domain, if you put the domain inside the function, right? So basically this ranges over all the elements in D, then all the numbers that you can get out of it is equal to f of D. So this is a bit of an abuse of notation, but this is normally how we write down the range of a function. Okay. So we're going to define the concept of continuity of a function. So we say, so let D be a subset of Rk, and let f be a function from D to real valued function from D to R. And then we say that f is continuous at x in the domain if the following holds. Well, for all sequences xn in the domain, if the sequence xn converges to x, which is this particular x at which f is continuous, well, then we have that f of xn converges to f of x. Okay, so for example, we have the sequence x1, x2, x3, and so on, and this converges to some vector x. Okay, so these are elements in the domain. So these are all elements on Rk. So if we map x1 to its function, then we have f of x1. If we map x2, then we have f of x2, and so on. f of x3, and these are all elements in R. All right, so basically this is a sequence of numbers in R, so it's possible that this converges to some number, right? So if f is continuous, then it will converge, and the thing it will converge to is exactly f of x. Okay, so let me give an example. Let x be be two-dimensional, so x1 could be let me call this the number y1 and the number z1, right? So it's a vector of 2 dimensions, one number and the second number. Then xn in general could be the vector y and zn. So this means that if this converges to some vector x, which we could denote by y and z, not vectors. Okay, so basically this means that the sequence yn converges to y and the sequence zn converges to z. Then if we say, for example, the function x is equal to function xn is equal to yn plus zn, right? So what do we do by using the function? We simply add the two arguments of the vector together. Well, then we see that if n goes to infinity, this goes to y plus z, which is exactly f of the limit. Okay, so here in this case, this function here, where you take the sum of the arguments, is clearly continuous. Okay, so but it's important to note that this is a sequence of vectors, right? And this talks about the sequence of convergence of numbers, right? The thing f points to. So this is a definition of continuity of a function. So in many handbooks, you also see the equivalent definition, which is the following, that f is continuous at an x in the domain if for all epsilon bigger than 0, there exists a delta bigger than 0, such that for all y in the domain, if the distance between x and y is smaller than delta, then f of x minus f of y distance is smaller than epsilon. Okay, so this is the famous or infamous epsilon delta definition of continuity, and you can show that it's equivalent actually to this one. So this is the definition that we really use most of the time when we talk about continuity of functions. So this is the definition for continuity at a particular point in the domain. Well, we say that f from some domain to the range is continuous if f is continuous at every x in the domain. Okay, so this is continuity at a certain point. If f is continuous at every point in D, right, so this definition is satisfied for every x in D, then we simply say that f is a continuous function. So if the domain would here be R, and then f of x, for example, if this is my x, then you can put f of x here. So in this case, this point here kind of depicts the function value at x. Then if you have a continuous function over the domain, this basically means that you do not lift your pen when you draw this function. Okay, so if you have a sequence of values that converge to x, then the function values, these points here, have to converge to this point here. So basically that's the graphical intuition behind continuity of a function. Okay, so we're going to prove an important fact or an equivalent definition of continuity of a function at a particular point. So this is going to be your theorem. So you have a domain in Rk, and you have a function from D to R, and then you have the following theorem that says that f is continuous at x in the domain if and only if the following holds. So for all sequences xn in D that converge to x, there exists a subsequence of the sequence here. So let's call it x phi n, such that f of x phi n this here converges to f of x. Okay, so f is continuous at a particular point. If for any sequence in D that converges to x, we can find the subsequence of this sequence such that f converges to f of x along this subsequence. Okay, so normally for continuity we had that for any sequence that converges to x, f of xn converges to f of x. So here we only require that for every sequence we can find a subsequence along which the convergence takes place. However, it appears, or the theorem at least claims, that these two definitions are equivalent. So what this says is that basically we only need convergence along a subsequence in order to formalize continuity of f at a certain point x. So this is an if and only if condition. So let's first do the easy part, and that's from here to here. Okay, so we need to show that for every sequence that converges to x we can find a subsequence along which f converges. So let's take any sequence xn in D such that xn converges to x. Okay, we have to find a subsequence x of phi n such that f of x phi n converges to f of x. So as a subsequence we can actually, because we know that f is continuous, we can take the function xn itself. So if we define the subsequence to be the sequence itself, then because f is continuous, we know that f of xn converges to f of x, which is exactly what we needed to show, right? So this proves the direction from the left to the right. Okay, so if f is continuous, then for any sequence that converges to x, we can find a subsequence that just that f converges along the subsequence. For example, we can take the sequence itself. And of course, we could have taken any other subsequence of the sequence, because continuity guarantees that because each of these subsequences converges to x, f of along the subsequence also converges to f of x. So the other direction is a bit more intricate, and we're going to use a proof by a contrapositive. Okay, so in order to prove that P implies Q, we're going to use the contrapositive. We're going to show that negative Q implies negative P. And here negative Q is the same as F is not continuous at X, and here negative P is, you have to switch the for all, so there exists a sequence xn in D such that xn converges to x, and then you have to negate this second part here, such that for all subsequences x phi n, f of x phi n does not converge to f of x. Okay, so this is what we need to show. We start from the fact that f is not continuous at x, and we need to find a sequence in D such that xn converges to x, and for all subsequences of the sequence f of xn does not converge. F of x phi n does not converge to f of x. So let's first have a look at this. What does it mean for f not to be continuous? So when f was continuous at x, we had that for any sequence in D, if the sequence converges to x, then f of x and converges to f of x. So you need to negate this formula here. We have that there exists a sequence xn in D such that xn converges to x and f of xn does not converge to f of x. Okay, so we start from this and then you have to show this. So in order to show this, we're going to use a previously established lemma that we have shown, I think, 2 videos ago. So this was the lemma, I hope you still recall it, is that if I have a sequence, let's say yn, then yn converges to y if and only if the following holds. For all subsequences y phi n, there exists a subsequence, right? So let me write this as y phi of psi n, such that this subsequence converges to y phi psi n converges to y. Okay, so a sequence converges, sequence of numbers, or it could be vectors, right? But let's take here numbers. A sequence of numbers converges to y if for any subsequence of the sequence I can find a subsequence that converges to y. And we're going to, so this is an if and only if, so we're going to negate both parts. Okay, so if you negate both parts, then we get that the sequence yn does not converge to y if and only if I can find a subsequence y phi n such that for all subsequences phi psi n this subsequence does not converge to y. Okay, yn doesn't converge to y if I can find a subsequence of the sequence such that no matter which subsequence I take from the subsequence, it will not converge to y. So we have proven this in one of the previous lectures, so we're going to use this result in order to prove our theorem. Okay, so let's go back to what we want to prove. So we want to show that not q implies not p. So remember, not q was that the sequence x converges to x, but f of x n does not converge to f of x. Okay, so we had the sequence xn converging to x, and f of xn did not converge to f of x. Now, f of xn is simply a number, and f of x is also simply a number. So let's write f of xn as yn, and let us denote the number f of x as y. Then this simply says that yn does not converge to y. Okay, so far I have done nothing new. I'm just redefining f of xn and f of x as yn and y. However, now we see that these two things are very similar, right? We have a sequence that converges to y, we have a sequence yn that doesn't converge to y. So using this, we can say that from this it follows that there exists a subsequence y phi n, okay, such that for any subsequence of the sequence, so for any y phi psi n, this subsequence does not converge to y. Okay. So here, let's have a closer look at the subsequence. Okay, so we know that y1 is equal to f of x1, y2 is equal to f of x2, y3 is equal to f of x3, and so on, and so on, and so on. So in general, we have that y phi n will be equal to f of x phi n. Okay, so for example, if phi of n is equal to 5, then y5 is equal to f of x5. So this is equal to x of phi 1. Okay, so, and then this sequence here, x phi n, is a subsequence of xn. Sorry. Okay. So x phi n is a subsequence of xn, and xn goes to x. So x of phi n goes to x. Okay. A subsequence of a sequence that converges to something also converges to the same thing. So let's summarize what we have here. Here we have a sequence x of phi n that converges to x. And for every y phi psi n, okay, so what's y phi psi n? Well, you know that y phi psi n is equal to f of x phi psi n. Okay, we just take the same sub-index for the y's and for the x's, and this gives you the correspondence between the y's and the x's. Okay, so if I go here, if I take here a subsequence of this amounts to taking a subsequence of this and then looking at the function values along this subsequence. Okay, so if I translate this for any subsequence of this subsequence, equally well I could take a subsequence x phi psi n, and then the fact that this does not converge to y is the same as saying that f of x phi psi n does not converge to f of x. Okay, so this is just placing y equal to f of x and y phi psi n equal to f of x phi psi 1 n. So here, going over all the subsequences of y is more or less equivalent to going over all the subsequences of the sequence here. And then we see that f along this subsequence does not converge to f of x. Okay. So if we go back to what we actually wanted to show, is that we can find a sequence in D that converges to x such that along every subsequence f along the subsequence does not converge to f of x. Here we have a sequence that converges to x, and for any subsequence of this sequence here, f along the subsequence does not converge to f of x. Right? So basically we have shown that this holds, negative p holds here for the sequence, and this sequence here is basically a subsequence of this sequence here. So this demonstrates the proof.